Hello there, and welcome to the Sleep Porch. Tonight, we'll be exploring the great unknown and uncovering some of the greatest mysteries in our universe. For all the progress science has made, there is still an immense frontier of unanswered questions. We have mapped galaxies, measured the faint glow of ancient light, and uncovered the behavior of particles far smaller than the eye can ever see. Yet every new discovery seems to uncover an even deeper layer of uncertainty. The universe guards its secrets well, and many of the ideas we rely on may be nothing more than stepping stones toward something far larger. Space may be stranger than our models allow. Time may not behave the way we imagine, and even the foundations of matter and energy might be fragments of a far grander design. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here as well, one sleepy soul at a time. But for now, all you need to do is relax. Take a slow, deep breath, let the day fall gently behind you, and allow your mind to settle into rest. Let's begin. The universe may hold regions forever hidden from our reach. Beyond the limits of what we can see, the universe expands into regions whose light will never reach us. Those distant regions are not just far away, they are cut off by the finite speed of light and the way space expands. Even if we built perfect instruments and waited longer than any human lifetime, some parts of reality would still remain out of reach. In those unseen domains, matter could arrange itself into galaxies and structures that never send a single photon in our direction. Physics might follow the same rules we know or twist them in subtle ways we cannot check. When we look at the night sky, we are staring at a small patch of a much larger whole, knowing that there are events happening right now, but no one here will ever witness. The universe may be full of stories that will forever remain untold. There could be entire realms of space with different laws of physics. Many modern theories suggest that what we call the laws of nature may not be uniquely fixed. Certain ideas in cosmology and fundamental physics allow constants like particle masses and interaction strengths to take different values in different regions of a larger reality. In one cosmic domain, stars might never ignite. In another, atoms might be unstable, or entirely different kinds of matter might form. We only know the behavior of our own patch, where the numbers happen to support long-lived stars and complex chemistry. It is possible that beyond any horizon, there are expanses where even the idea of a stable atom would be impossible. Our familiar physics could be a local dialect spoken in a much larger landscape of possibilities. If that is true, then what we call fundamental might be more like a regional custom, one example among many, with no way for us to visit the others and compare. We still do not know what happened before the first moment of time. Our best cosmological models describe how the universe evolved from an early hot and dense state, but they do not fully explain what, if anything, came before. At very early times, gravity and quantum physics must both matter. Yet we do not yet have a single theory that combines them consistently. When we run the equations backward, they eventually stop giving meaningful answers, as if the mathematical surface of time itself ends. Some proposals suggest a prior contracting phase. Others imagine a bounce, and some describe time as emerging from something more primitive that does not resemble ordinary before and after. Observations of the sky give us clues about the early fireball, but they cannot directly pierce whatever lies beyond that veil. The question of a beginning may even be the wrong way to think about it. Yet our minds are drawn to it. What does it mean for time to start? And can there ever be a reason for the first instant? Space might be infinite, or it might loop back on itself. When we look out into the cosmos, we can measure how space is curved on vast scales. But those measurements do not yet tell us the global shape of everything. One possibility is that space extends without limit, stretching on forever with no boundary and never returning to where it started. Another is that space has a finite volume but no edge, like the surface of a sphere generalized into more dimensions. So that if you could travel far enough in one direction, you might eventually return to your starting dasher point. Different shapes of space would subtly change the pattern of structures we see in the sky. But those differences are extremely delicate and hard to detect. Our observations so far are consistent with many possibilities. The true shape of all that exists could be simpler or stranger than we imagine, and we may never travel far enough to find out for certain. There could be invisible dimensions interwoven with the ones we see. We experience reality as having 3 directions of space and 1 of time. But some theories that try to unify the forces of nature work only if additional spatial directions exist. These extra directions could be curled up to sizes unimaginably small so that we do not notice them in daily life. Their presence could gently affect how particles move and how gravity behaves, leaving only subtle traces in experiments and cosmic observations. In such a picture, every point in familiar space would really be a tiny, multidimensional structure with paths that loop through directions our senses cannot follow. If these hidden dimensions exist, they might allow new kinds of particles or even connect distant regions of space in ways we have barely begun to picture. Looking for them requires creative experiments and careful study of how the universe evolved. The idea that our world might be only part of a larger dimensional tapestry remains an open and profound possibility. We do not know what space itself is made of. We talk about space as if it were an empty stage, a smooth backdrop where matter moves and light travels. Yet, we do not truly understand whether that stage is fundamental or built from something deeper. Some approaches to quantum gravity picture space as emerging from discrete building blocks, perhaps a network of relations or tiny units of area and volume that only look continuous from far away. Others imagine space arising from patterns of quantum information, like a vast web of entanglement that gives rise to distance and geometry as collective effects. Even in ordinary physics, vacuum is not truly empty, but filled with fluctuating fields that can give rise to real particles. These hints suggest that the notion of a simple void may be an illusion. If space has an underlying structure, then at extremely small scales, our familiar concepts of location and distance might dissolve, replaced by something that does not fit our usual intuition. Time may flow differently in parts of the universe we cannot reach. Relativity tells us that the passage of time is not absolute. It depends on motion and on gravity. Clocks deep in gravitational wells tick more slowly compared to clocks far away. And objects moving at high speeds experience less elapsed time than those at rest. Across the universe, matter is arranged in complex ways, from dense clusters to vast empty regions. So the rate of time can vary from place to place. In distant galaxies, the rhythm of processes could be slightly offset from our own, even if no one there would notice the difference locally. In extreme environments, near very compact objects, the difference becomes even more dramatic. with outside observers watching events unfold in slow motion. Because we cannot synchronize clocks across unreachable distances, we are left with a patchwork of local times woven together by theory. The idea that there is a single, universal now becomes difficult to sustain once we take the cosmos into account. The universe might be one bubble among countless others. Some theories of cosmic inflation suggest that the universe's early, rapid expansion may not have ended everywhere at the same moment. In certain regions, the expansion could have slowed and cooled, creating bubbles where conditions stabilized enough for galaxies and stars to form. In other regions, the runaway growth may have continued, spawning new bubbles, each with its own unique physical properties. In this view, our observable universe is just one of those bubbles, a finite pocket floating within a much larger, still inflating expanse. Other bubbles might never touch ours, remaining forever isolated, separated by vast distances and by regions of space that continue to stretch at unimaginable speeds. Within those distant domains, physics might take different forms, or perhaps echo our own in ways we will never confirm. This picture turns what we call the universe into one example inside a greater multiverse. It offers explanations for certain cosmic puzzles, yet raises even deeper questions about what counts as reality. There could be structures larger than anything we can observe. Astronomers have discovered clusters, filaments, and sheets of galaxies that span astonishing distances, weaving a cosmic web through space. Yet our surveys are limited by how far light has traveled since the early universe, and by the parts of the sky we have been able to study in detail. It is entirely possible that beyond the boundaries of current data, there are arrangements of matter even grander than the largest known formations. Perhaps superstructures that bend our assumptions about outbreak. Uniform the cosmos should be. Some hints already challenge expectations, such as huge alignments that appear more coherent than standard models predict. Whether these are statistical flukes or glimpses of something deeper remains uncertain. If truly colossal structures exist beyond our horizon, their gravity could influence the motion of galaxies we do see, leaving only indirect signs of their presence. In that sense, unseen architecture might be quietly shaping the cosmos we can measure. We do not know whether the universe has an edge or no boundary at all. When we talk about the universe, it is natural to picture a region with some kind of border beyond which there is nothing. Yet in physics, the idea of an edge to space is problematic because edges usually imply something outside. One alternative is that the universe is finite but curved in such a way that it has no boundary, like the surface of a sphere that ends nowhere, even though it has limited area. Another possibility is that space extends indefinitely, with no edge and no outside, only more and more of the same fabric. Our observations of the cosmic background and the distribution of galaxies tell us about geometry within the part we can see, but they do not conclusively answer the global question. Even our language struggles because we are trying to describe the totality of everything from within. Whether there is a true edge, a closed shape, or infinite extent remains one of the deepest open puzzles. The universe might be expanding into something we cannot perceive. When we measure the motion of distant galaxies, we find that space itself is stretching, carrying them farther from us. Yet the question of what this expansion is happening into remains unresolved. In standard cosmology, space does not need an outside. It can grow the way a pattern on a balloon grows, even if you focus only on the two-dimensional surface without considering the air around it. Still, it is difficult not to wonder whether the fabric of the cosmos is embedded in something larger. If such an external realm exists, it would not necessarily follow the rules of our own space or time. It might not contain matter, energy, or geometry as we understand them. Our instruments are designed to measure what happens within the universe, not beyond it. As a result, any wider container would remain hidden from view, leaving us to infer possibilities only through mathematics and the behavior of distant galaxies. The true nature of expansion remains one of the most puzzling questions in modern science. We still do not understand why space is so smooth on vast scales. Across billions of light years, the universe looks remarkably uniform. The temperature of ancient radiation varies only by tiny fractions, and matter spreads out in a pattern far more even than one might expect. This smoothness is surprising because regions separated by extreme distances could never have interacted in the early universe. There was simply not enough time for light or any other signal to travel between them. To explain this, theories propose a brief phase of extremely rapid growth that allowed regions now far apart to originate from a small, connected area. Although this idea fits the data well, we still do not know what triggered that growth, how it ended, or whether alternative explanations might work. The uniformity we observe could carry information about processes that occurred before the earliest moments we can probe. Space may hold silent clues about a deeper mechanism that shaped the entire cosmos long before galaxies began to form. The universe could carry subtle imprints from events before its birth. The oldest light in the universe is a faint glow that has traveled across space for almost the entire cosmic history. Although it has been studied with great precision, it might contain traces of processes that happened even earlier than the hot, dense state usually described as the beginning. Certain models of cosmic evolution predict that ripples, patterns, or slight distortions might survive from an earlier phase, carried forward as the universe expanded and cooled. These features would be extremely delicate, hidden within the noise of cosmic data, and difficult to distinguish from ordinary fluctuations. If they exist, they could reveal information about conditions that no current experiment can recreate. They might hint at a prior contraction or a more complex transition that preceded the familiar expansion. The possibility that our universe retains the fingerprints of an earlier era invites the idea that the cosmos has a longer and richer story than we can presently observe. There may be hidden patterns in the cosmic web we have not recognized. When astronomers map the distribution of galaxies, they discover a sprawling network of clusters, filaments, and great empty voids. This intricate web resembles the structure of living tissue or neural pathways, showing how gravity shaped matter on the largest scales. Yet we may only be seeing the most obvious layer. Deeper mathematical relationships might link the positions and motions of galaxies in ways we have not yet noticed. Subtle symmetries could be present in the alignment of structures, or long-range correlations might exist that require new tools to detect. Even the way galaxies rotate or cluster might follow hidden rules that have gone unrecognized. As surveys grow more detailed, they may reveal unexpected organization buried within the apparent randomness. Patterns like these could hint at undiscovered physics or at early cosmic processes that left long-lasting effects throughout the web of matter that stretches across the universe. The universe might end in ways we cannot yet imagine. Cosmology offers several possible futures, yet none are certain. If dark energy remains steady, space will continue expanding at an ever-increasing rate, gradually isolating galaxies from one another until the night sky grows empty and cold. If dark energy strengthens, the expansion could accelerate so dramatically that even atoms might eventually be pulled apart. If dark energy weakens or reverses, the universe could slow, halt, and collapse into a dense state, possibly leading to a new expansion. Other possibilities involve transitions in the underlying vacuum of space, changes in physical laws or processes we have not yet formulated. Because we cannot measure the future behavior of dark energy or the stability of the vacuum, we face fundamental uncertainty about how the story of the universe concludes. Each scenario shapes matter and time in profoundly different ways. The vast future remains an open landscape of possibilities, each hinting that our cosmic era is only one chapter in a much longer narrative. They could be cycles of cosmic creation beyond our horizon. Some theoretical frameworks imagine that the universe did not begin with a single event, but instead passes through repeating phases of contraction and expansion. In such a picture, our own cosmic history would be part of a larger sequence, with previous cycles imprinting subtle hints on the structure we observe today. Although these ideas are difficult to test, they offer explanations for certain puzzles about uniformity and fine structure. If the universe has experienced multiple cycles, then each era might inherit conditions shaped by those that came before. Entire sequences of galaxies, stars, and cosmic evolution could have risen and faded long before our own epoch, leaving few traces except possibly in the earliest moments of the current expansion. These cycles might continue far into the future, forming a grand rhythm of creation and transformation that lies beyond our observable domain. Whether such patterns truly exist remains unknown, yet they provide a striking alternative to a single beginning. We do not know what started the rapid expansion of the early universe. Observations strongly support the idea that the universe underwent a brief period of extremely fast growth shortly after its earliest moments. This expansion smoothed out irregularities and set the stage for the formation of galaxies. However, the cause of this rapid growth remains mysterious. Proposed explanations include new fields of energy, transitions between physical states, or deeper mechanisms that might involve the fabric of space itself. Each proposal attempts to account for the characteristics we see today in ancient radiation and the arrangement of matter. Yet, none has been confirmed, and several predict effects that are very subtle. Without a way to directly examine the conditions of that early time, we must rely on indirect clues and careful analysis of cosmic patterns. The true trigger of this expansion remains an open question, and understanding it may require insights that unify ideas about gravity, quantum physics, and the origin of space. The universe might have dimensions curled too small to detect. Some theories that aim to unify the forces of nature suggest that in addition to the familiar three dimensions of space, there may be extra directions folded into extremely tiny shapes. These compact dimensions would be far smaller than any current experiment can probe, hidden within the structure of each point in space. Their geometry could influence particle behavior, alter gravitational interactions, or allow new types of motion that cannot occur in ordinary space. Although these dimensions would not be directly visible, their presence might produce small deviations in measurements of particle collisions, or leave faint signatures in the early universe. Searching for these effects requires precise instruments and creative experimental designs. If such curled dimensions exist, it would imply that our everyday experience, the universe, might be built on a multidimensional foundation, that remains almost entirely concealed. We do not know whether space emerges from something deeper. Modern research has raised the possibility that space is not a fundamental entity, but instead arises from more basic components. In some models, geometry is produced by patterns of quantum information or by networks of relationships between microscopic elements, but do not resemble locations in any ordinary sense. Distances, directions, and even the flow of time could be large-scale consequences of these underlying structures. Evidence for such ideas comes from studies of black holes and quantum physics, where traditional concepts break down and new principles appear to link geometry with information. Although these ideas are still speculative, they offer a route toward unifying gravity with the world of particles. If space is emergent, then familiar reality might be analogous to a surface formed from countless unseen interactions. Understanding the deeper layer could change the way we think about the fabric of the universe and the nature of existence itself. The universe could be a projection of a more fundamental reality. Certain approaches to quantum gravity suggest that the three-dimensional world we experience may be encoded on a lower dimensional structure, somewhat like a hologram. In these proposals, the full richness of space and matter arises from information stored on a surface that has fewer dimensions than the space it describes. This concept emerged from the study of black holes, where the amount of information needed to describe them seems to scale with their surface area rather than their volume. Extending this idea to the entire cosmos suggests that reality might have an unexpected architectural design. Although this does not mean the universe is an illusion. If dark energy changes, it could reshape the cosmos's final destiny, either strengthening and pushing galaxies apart even faster, or weakening enough for gravity to slow the expansion in the distant future. It may even undergo transitions, behaving differently in earlier epochs than it does today. The challenge is that dark energy does not interact directly with matter or light. We detect it only through the motions of galaxies and the geometry of space itself. Although many theories attempt to explain it using new particles, another possibility is that dark matter does not belong to the familiar family of forces and interactions at all. It could arise from a sector of physics that barely touches the one we experience. In such a scenario, dark matter might have its own kinds of particles, motions, and internal processes operating in a shadow-like framework that rarely influences ordinary matter except through gravity. This idea opens the door to entire worlds of behavior that remain hidden from every detector on Earth. If dark matter truly lies outside known physics, then solving its nature will require ideas beyond the standard approaches. Its presence could be a clue. Some are familiar, such as neutrinos, which pass through matter with little interaction. Others may exist beyond our current understanding. These hypothetical particles could permeate the cosmos, drifting through planets, stars, and living beings without leaving detectable traces. Their interactions might be so weak or so unusual that they escape every current instrument. Some theorists predict particles that rarely collide with normal atoms, while others propose entities that do not fit the usual categories of matter and energy. Dark matter could form structures as complex as the visible universe. Although dark matter is invisible, its gravity affects everything around it. Models of cosmic evolution often show dark matter gathering into halos that guide the formation of galaxies. Yet these halos might not be simple clouds. They could contain layers, clumps, waves, or patterns shaped by interactions within the dark sector. If dark matter has its own forces or particle families, it might be capable of forming structures as varied as those made of atoms. The idea that an unseen architecture coexists alongside the visible cosmos highlights how limited our perspective may be. Dark energy might interact with matter in ways we have not observed. Most interpretations treat dark energy as something that influences only the expansion of space, not the behavior of matter. However, some theoretical models allow for a faint connection between dark energy and the particles that make up stars and galaxies. Future surveys that examine distant galaxies more precisely may reveal signs of the hidden dialogue between dark energy and matter. If dark energy reflects a hidden layer of reality, then our familiar understanding of space might be only a surface-level description. The behavior of dark energy could reveal information about this deeper framework. Yet, we currently lack the tools to probe it directly. Observations of distant supernova, galaxy clustering, and the cosmic background provide clues, but the full picture remains obscure. Dark energy may be the most accessible sign that reality contains levels we have not uncovered. Dark matter might be a shadow of processes in higher dimensions. Some theoretical models propose that our universe contains more spatial directions than we can perceive. If higher dimensions exist, dark matter might be an echo of processes occurring within them. In this view, particles we detect only through gravity might be objects moving or interacting in directions unseen by ordinary senses. Their apparent invisibility could be a natural consequence of their higher dimensional nature. These particles would interact only weakly with familiar matter because they occupy different slices of reality. Yet their mass would still tug on stars and galaxies. This idea could explain why dark matter behaves so differently from ordinary particles, and why it forms vast halos around galaxies. Detecting such effects would require searching for tiny deviations in gravitational behavior or looking for hints of motion through extra dimensions. If dark matter is truly connected to higher dimensions, uncovering its nature would transform our understanding of what space itself can be. Some theories even suggest the existence of entire stars made mostly of dark matter. If dark matter can clump under gravity, it could gather into dense concentrations, compact objects that behave like stars but without nuclear reactions or visible light. These dark stars would be practically invisible to telescopes that rely on electromagnetic radiation. Instead, their presence might be revealed through gravitational influence alone. Some theories imagine dark matter particles that can release energy through exotic interactions, allowing dark stars to shine faintly in ways we have not yet identified. Others picture them as cold, quiet bodies drifting through galaxies, leaving only subtle gravitational footprints. Finding such objects would require precise mapping of stellar motions or gravitational lensing. The existence of dark stars would add an entirely new category to the cosmic inventory, showing that the universe contains kinds of stellar bodies fundamentally different from anything we have ever seen. Dark matter might carry information about ancient cosmic eras. Because dark matter interacts so little with ordinary particles, it has preserved its original properties across almost the entire history of the universe. While atoms were broken apart, fused, and reshaped in stars, dark matter remained largely unchanged. Its distribution today still reflects the conditions that existed long before galaxies formed. If we could decode its structure, we might learn about epochs that no radiation can directly reveal. For example, slight variations in dark matter density might reflect events in the very early universe, or transitions that occurred before familiar particles emerged. Mapping these patterns requires detailed observations of how galaxies move within their halos and how matter clusters on different scales. Each measurement provides a hint of the ancient landscape that shaped the cosmos. Dark matter serves as a quiet record keeper of eras beyond direct observation, storing information in the way it is arranged across space. Black holes may contain regions where the fabric of reality breaks down. When matter collapses under its own gravity and forms a black hole, the equations of general relativity predict that space-time curves more and more sharply toward the center. At some point, these equations indicate that curvature becomes infinite. This is a sign not of a literal infinity, but of the failure of our current theories. Near such extreme conditions, the familiar rules of space, time, and physics may dissolve. Quantum effects should become important, yet we do not have a complete theory that unites quantum mechanics with gravity. As a result, the interior of a black hole remains an unsolved frontier. Physical quantities that behave smoothly elsewhere may no longer make sense. Even the concept of location could break down. This mysterious region is hidden from the outside world by the event horizon, so no signal can carry direct information outward. The unknown interior remains one of the most dramatic reminders that our understanding of reality is incomplete.
A black hole's center could be something other than a singularity. Although classical theory predicts a point of infinite density at the core of a black hole, many researchers believe that nature avoids true infinities. Alternative models propose that quantum effects could replace the singularity with something more complex. Some ideas picture a region of extremely high but finite density. Others describe a tiny sphere where quantum pressure counteracts gravity. Still others imagine a surface where space-time undergoes a phase transition. These possibilities depend on how quantum gravity operates. And since that field remains under development, no single answer has emerged. Observations of black holes do not reveal their centers, so indirect evidence must be used. The behavior of gravitational waves, the motion of matter near the event horizon, and the stability of black holes over long periods may offer clues. Each scenario implies a different internal structure, suggesting that black holes might contain exotic states of matter or geometry unlike anything we have studied in laboratories. There might be paths through black holes that lead elsewhere. The mathematics of general relativity allows solutions where black holes connect to distant locations, or even other universes through hypothetical bridges. These structures are often unstable and may collapse too quickly for anything to pass through, yet they remain intriguing possibilities. If quantum effects modify the interior, such pathways might become more stable. In certain models, a traveler attempting to cross would face enormous tidal forces and unpredictable physical conditions, making any journey purely theoretical for now. Some theories propose that what appears to be a black hole from the outside could be connected to a different region that looks like a white hole from within, ejecting matter instead of absorbing it. These concepts arise naturally in the equations of gravity. Yet we lack evidence to determine whether any of them correspond to real physical objects. Even so, the idea that black holes might serve as gateways hints at a universe more interconnected than our senses suggest. Black holes could store information in ways we do not understand. A long-standing puzzle in physics concerns what happens to information carried by matter that falls into a black hole. Quantum theory insists that information cannot be destroyed. Yet classical black holes appear to erase the details of anything that enters. Efforts to resolve this contradiction have led to the idea that information might be encoded in subtle patterns on the event horizon, or stored in quantum states of the gravitational field. Some proposals suggest that the horizon behaves like a physical surface with an enormous number. Others propose that information is released slowly through radiation during the black hole's lifetime. None of these ideas are fully proven, and each raises new questions about how information is represented in space-time. The resolution of this puzzle could reveal a deeper connection between quantum theory and gravity, showing how the universe preserves its history even in the most extreme environments. There might be tiny primordial black holes scattered through the cosmos.
In the very early universe, density fluctuations could have been large enough in some regions to collapse directly into small black holes. These primordial objects would not have formed from stars, so their masses could range from extremely small to quite large. If they exist, they might contribute to dark matter or influence cosmic evolution in subtle ways. Some might have evaporated completely, while others could still drift through galaxies invisibly. Their presence might be revealed through gravitational lensing of distant stars, through disruptions in the motions of objects, or through faint radiation produced during their final stages of evaporation. Despite careful searches, no confirmed detection has yet been made. The possibility of primordial black holes remains open, offering a link between the physics of the early universe and the dark matter puzzle. If they are real, they would provide a direct window into conditions that existed long before the first stars formed. We do not know what happens at the very edge of a black hole. The boundary that separates the interior of a black hole from the outside universe is called the event horizon. It is not a solid surface, but a region where escape becomes impossible. Although general relativity predicts how the horizon behaves, quantum effects complicate the picture. According to theory, the horizon emits radiation due to quantum processes, yet the detailed mechanism remains unclear. Some research suggests that the horizon might have a complex structure influenced by quantum information. Others picture it as a smooth boundary with no special features. Because we cannot observe the horizon up close, our understanding relies heavily on theory. The behavior of particles, light, and information near this boundary may hold clues about the unification of physics. The end of a black hole is a frontier where known laws reach their limits, making it a key area of study for anyone seeking a deeper understanding of gravity and quantum mechanics. Black holes could evaporate in ways we have never observed. Quantum theory predicts that black holes emit radiation, slowly losing mass over extremely long timescales. This process, while theoretically robust, has never been directly observed because even small black holes evaporate far too slowly for current detectors. Some models suggest that evaporation might include bursts of energy or changes in the spectrum of the emitted radiation at late stages. Others propose that the final moments could reveal new physics involving exotic particles or transitions in the nature of spacetime. If evaporation proceeds differently from the standard picture, it could alter our understanding of energy conservation, information preservation, and the life cycle of black holes. Detecting these signals would require either an unexpectedly small black hole near Earth or a new method for observing extremely faint radiation across the cosmos. The final fate of black holes remains an open question, one with profound implications for the nature of the universe. Some black holes might have formed before the first stars existed. Most black holes arise from massive stars collapsing at the end of their lives. However, conditions in the early universe may have allowed black holes to form directly from dense regions of primordial gas. These black holes would predate the first stars and galaxies, acting as seeds that influenced early cosmic structure. Their growth could help explain how some supermassive black holes became so large so quickly, an ongoing puzzle in astronomy. Early black holes might have interacted with the surrounding gas, altering the rate at which the first stars formed. Observations of ancient quasars reveal extremely massive black holes at times when the universe was still very young. Understanding how these giants arose may require the existence of an earlier generation of black holes formed through mechanisms unrelated to stellar evolution. These ancient objects would provide insight into the earliest chapters of cosmic history. Black holes could shape the universe more than we realize. Although black holes are often pictured as isolated objects, Their influence extends far beyond their immediate surroundings. The largest galaxies appear to have enormous black holes at their centers, and the energy released by matter falling into these giants can shape the growth of the entire galaxy. Jets of high-energy particles can heat or disperse gas, regulating star formation across vast regions. Even smaller black holes can influence their environments by triggering bursts of radiation or stirring the motion of nearby matter. On cosmic scales, the collective activity of black holes may affect how structures evolve, how galaxies cluster, and how gas circulates between regions. Even these subtle, indirect effects can reshape whole regions of space across immense stretches of time. The role of black holes in cosmic evolution is still being revealed, suggesting they are not merely the endpoints of stellar life, but engines capable of driving large-scale transformations. And many may be hidden black holes that emit almost no light at all. Most of the ones we know about are discovered through the radiation produced by hot gas spiraling inward. But countless others may exist in quiet regions where almost no matter falls into them. These black holes would be nearly invisible, detectable only through their gravitational influence. Some may drift alone through interstellar space, others might linger in the outer parts of galaxies or nestle within star clusters. Finding them requires careful study of stellar motions, gravitational lensing, or rare interactions with nearby objects. The universe could contain far more black holes than current observations suggest, with many remaining invisible. These silent black holes hold clues about stellar evolution, galactic dynamics, and the unseen population of remnants scattered throughout the cosmos. The existence reminds us that much of the universe may be made of objects that reveal themselves only through subtle gravitational effects. Gravity might behave differently on scales larger than galaxies. Astronomers have measured gravity with great precision within our solar system and inside galaxies. Yet on the vastest scales, it becomes far more difficult to determine whether the familiar equations still apply. The motion of galaxies within clusters, the rate at which large structures grow, and the pattern of ancient cosmic light all depend on gravity acting across immense distances. Some observations hint at slight mismatches between predictions and reality, suggesting that gravity might change its behavior very subtly when stretched over enormous scales. These variations could be tiny, yet influential enough to affect the expansion of the universe or the formation of cosmic structures. Several ideas propose that gravity may weaken, strengthen, or shift its form when dealing with the emptiest regions of space. Others suggest that modifications might occur because the universe is not perfectly uniform. Untangling these possibilities requires deeper surveys, more refined models, and new ways of testing gravity across cosmic landscapes far larger than anything accessible in laboratories. They could be hidden forces acting across cosmic distances. In addition to gravity, the universe may host long-range forces that barely affect everyday matter, but shape the cosmos in subtle ways. These hypothetical forces could influence how galaxies move or how clusters evolve. They might act extremely weakly, making them difficult to detect within the solar system, yet influential across billions of light years. Some theories predict that these forces emerge from new fields that fill all of space, guiding the behavior of dark matter or interacting with matter only through delicate channels. Such forces could help explain unusual motions within galaxies or unexpected patterns in cosmic structure. Detecting them would require precise observations of distant objects, careful comparison with theoretical predictions, and the willingness to consider that the universe might include influences far beyond the familiar pamper. 4 fundamental interactions. If hidden forces exist, they would reveal an enriched and more intricate picture of cosmic behavior. Gravity might be linked to quantum information in a way we do not yet see. Ideas from quantum theory and general relativity increasingly suggest that space-time might be connected to the flow of information. In some approaches, the curvature of space could emerge from the structure of microscopic quantum states, with gravity arising as a large-scale consequence of how information is organized. This perspective connects the bending of light, the motion of planets, and the behavior of black holes to deeper patterns involving entanglement and quantum correlations. If this link is real, then classical gravity might be the visible expression of an underlying informationational fabric. Evidence for these ideas comes from studies of black hole thermodynamics and from mathematical correspondences between geometry and quantum systems. Yet no direct experiment has confirmed the connection. Understanding it may require entirely new tools that bridge the gap between quantum physics and gravity. This possibility hints that the universe's geometry may not be fundamental, but instead a reflection of hidden formational rules. The universe could contain gravitational phenomena we have not imagined. Most of our understanding of gravity comes from observing planets, stars, black holes, and large-scale structures. Yet the universe is vast enough that phenomena unknown to us may occur under extreme conditions or in regions we have not yet explored. There might be exotic gravitational configurations where space-time behaves in ways not described by simple curvature. Strange objects could exist that bend space in asymmetrical or unpredictable patterns. Regions with unusual forms of matter might produce entirely new gravitational effects that have left only faint or indirect signs in observable data. As our instruments improve, we may uncover hints of these unfamiliar behaviors, perhaps in gravitational wave signals or in anomalies found in the distribution of distant galaxies. The full diversity of gravitational possibilities may extend well beyond our current theories, waiting to be discovered in the deep reaches of the cosmos. There might be regions where gravity temporarily weakens or strengthens. The strength of gravity is usually treated as constant, yet in some theoretical frameworks, it could vary slightly in time or space. These variations might arise from fields that evolve slowly across cosmic distances, or from interactions between gravity and unknown components of the universe. If gravity fluctuates gently, these changes would be far too small to notice on Earth, but they could influence cosmic evolution over immense periods. Regions where gravity is slightly stronger might form structures earlier, while weaker regions might delay the growth of galaxies. Observations of distant clusters and the cosmic web may hold subtle signs of such variations. Distinguishing them from ordinary cosmic variability is challenging, requiring careful analysis of large datasets and sophisticated simulations. If gravity does shift in strength, even by tiny margins, it would imply a deeper and more dynamic foundation underlying one of nature's most familiar forces. Gravity could leak into dimensions beyond our own. Some theories propose that gravity might not be confined to the familiar three-dimensional space we inhabit. Instead, it could spread into additional spatial directions that are hidden from ordinary perception. If so, gravity would appear weaker than expected in our three-dimensional world because part of its influence would extend into these unseen directions. This idea could help explain why gravity is so much weaker than other forces.
It might also produce distinctive patterns in experiments designed to detect tiny deviations from Newtonian behavior. On cosmic scales, gravity leaking into higher dimensions could influence the rate at which structures grow or contribute to the accelerated expansion of the universe.
Although no conclusive evidence has been found, the possibility remains compelling because it integrates naturally with theories that attempt to unify the fundamental interactions. Discovering extra-dimensional effects would reshape our understanding of space, matter, and the behavior of the cosmos. The gravitational constant might not be constant everywhere. The constant that sets the strength of gravity plays a central role in every astronomical calculation. Yet we do not know whether it is truly fixed across space and time. If it varies even slightly, it could influence the formation of stars, the behavior of galaxies, and the evolution of the universe. Subtle shifts might occur due to interactions with unknown fields, or due to processes that began in the early universe. Observations of distant objects offer indirect tests, yet distinguishing true variation from ordinary astrophysical differences is extremely challenging. Some studies have searched for signs in the timing of pulsars, the brightness of supernova, or the distribution of galaxy clusters. So far, results remain inconclusive. If future measurements reveal that the gravitational constant changes, it would indicate that gravity is not a simple universal force, but a dynamic quantity shaped by deeper layers of physics. The way gravity works near the beginning of time is still unknown. As we trace cosmic history backward, conditions become increasingly extreme. Temperatures rise, densities climb, and quantum effects become significant. Under such circumstances, general relativity alone cannot describe gravity. We need a theory that unifies gravity with quantum physics. Yet that theory remains incomplete. Without it, we cannot fully understand how space curved or how matter behaved during the earliest moments after the beginning of the universe. Clues may be hidden in the pattern of ancient cosmic light, in the distribution of large-scale structures, or in the behavior of gravitational waves. These hints suggest that gravity may have operated differently at that time, perhaps allowing phenomena that no longer occur. The early universe represents a laboratory with conditions impossible to recreate on Earth. Understanding gravity in that environment remains one of the most pressing challenges in cosmology. There could be particles that mediate gravity in subtle ways. In quantum field theory, forces are often transmitted by particles. If gravity follows a similar pattern, it might be mediated by a hypothetical particle. Such a particle would interact extremely weakly, making it nearly impossible to detect in experiments. Its existence could influence gravitational waves, modify the behavior of black holes, or subtly affect how matter clusters on large scales. Some theories predict families of such particles, each contributing in different ways to the overall behavior of gravity. Detecting them would require methods capable of isolating incredibly faint signals or observing effects that accumulate over cosmic distances. These particles may also interact with unknown fields or dimensions, complicating their behavior. If they exist, they would provide a direct route toward unifying gravity with quantum theory, revealing the microscopic structure behind the force that shapes the cosmos. Gravity might arise from something deeper than spacetime. The familiar picture of gravity as the curvature of spacetime may be an approximation of a more fundamental process. In some models, gravity emerges from the collected behavior of microscopic constituents that do not resemble space at all. These constituents could be quantum bits of information, relational structures, or other entities that operate according to rules unlike any classical theory. Space-time itself would then be a large-scale phenomenon, much like temperature arises from microscopic motion. If gravity is emergent, then understanding its true nature requires identifying the underlying components and the principles that govern them. Evidence for this idea comes from connections between thermodynamics, information theory, and black hole physics. Although still speculative, the concept offers a unified way to link gravity with quantum mechanics. It suggests that our sense of space, time, and curvature may be secondary effects shaped by an unseen foundation that determines how the universe behaves at its deepest level. The first stars may have been unlike anything in the modern universe. Astronomers believe the earliest stars formed from pristine gas containing only hydrogen and helium, the simplest elements created in the first minutes of cosmic history. Without heavier elements to cool the gas efficiently, these stars may have grown far more massive than anything that typically forms today. Some theories suggest that they reached hundreds of times the mass of the Sun, burning at extraordinary temperatures and living for only brief periods before collapsing or exploding. Their interiors may have produced the first heavy elements, seeding later generations of stars and shaping the chemistry of the universe. Because these earliest giants lived fast and died young, they vanished long before any galaxy reached maturity. Detecting traces of them requires studying faint signals imprinted on ancient cosmic light or observing extremely distant galaxies where their influence remains embedded in the distribution of gas. The nature of these first stars remains unknown, yet they set the stage for everything that followed. We do not know how the first galaxies formed so quickly.
When telescopes peer back into very early cosmic times, they reveal galaxies that appear surprisingly mature despite the short interval since the first stars ignited. These early galaxies contain structured regions, vigorous star formation, and sometimes even central black holes. Standard models predict that assembling such complex systems should require longer periods than the universe appears to have given them. This mismatch has prompted renewed study of how gas collapses, fragments, and ignites under primordial conditions. It also raises questions about whether our theories correctly describe how matter behaved during the first few 100 million years. New observations continue to find surprisingly bright and organized early galaxies, deepening the puzzle. These discoveries hint that early cosmic environments may have fostered rapid growth through processes not yet fully captured in simulations. The first galaxies remain key to understanding how the large-scale structure of the universe emerged from initial fluctuations. Some ancient galaxies look far older than they should be. Observations of extremely distant galaxies sometimes reveal systems that appear too massive, too bright, or too chemically enriched for their age. These galaxies were born when the universe was still in its infancy, yet they carry features we would expect only in much later eras. Their stars show hints of earlier generations, even though by conventional timelines, there should not have been enough time for multiple cycles of birth and evolution. This tension challenges existing models of galaxy growth, encouraging scientists to ask whether star formation was far more efficient in the early universe or whether unknown mechanisms sped up their development. Some of these galaxies may have undergone rapid mergers, while others might have collapsed unusually quickly from dense pockets of primordial gas. Each possibility carries deep implications for cosmology, hinting that our understanding of early cosmic timelines may need refinement. These ancient outliers stand as powerful reminders of the unexplained processes that shaped the universe's very first structures. They could be stars made almost entirely from exotic particles. Most stars shine through nuclear fusion of familiar elements, but some theories propose the existence of stars composed partly or entirely of exotic forms of matter. These hypothetical objects might use dark matter interactions as an energy source. Or they might consist of particles that do not follow the usual rules of nuclear physics. If such stars exist, they would behave differently from ordinary ones.
Their temperatures, lifetimes, and internal structures could diverge dramatically from standard expectations. They might emit unusual spectra or produce neutrino signatures unlike any known stellar process. Detecting them would require careful searches for stars that appear too dim, too bright, or too stable for their mass and age. These exotic stars would offer direct insights into unfamiliar physics, showing that starlight may not always come from the same kinds of processes that power the familiar cosmos. We do not know how supermassive black holes grew so fast. Giant black holes, millions or billions of times the mass of the Sun, exist in galaxies throughout the universe. Yet observations show that some of these giants were already enormous when the universe was still very young. Their rapid growth poses a challenge because known processes of accretion and merging do not seem efficient enough to build such massive objects so quickly. Several ideas attempt to resolve this puzzle. Some propose that the first black holes formed from stars far larger than any seen today. Others suggest that entire clouds of gas may have collapsed directly into black holes without forming stars first. Another possibility is that early environments allowed unusually rapid feeding rates. Each explanation requires conditions that differ from those found in the modern universe. Understanding how these giants emerged so early is essential because they influenced the evolution of the first galaxies and shaped large-scale cosmic development. Some galaxies appear to lack dark matter for reasons we cannot explain. Dark matter is thought to be essential for galaxy formation, providing the gravitational framework that holds stars and gas together. Yet, a handful of observed galaxies seem to contain far less dark matter than expected, and in some cases, almost none at all. Their stars move more slowly than predicted, suggesting that dark matter does not dominate their mass. These unusual systems challenge widely accepted ideas about how galaxies form and evolve. Some hypotheses propose that interactions with neighboring galaxies stripped away dark matter, while others suggest that these galaxies may have formed through processes not yet understood. Observing them more closely may reveal whether they truly defy expectations, or whether hidden complexities in their structure mask the presence of dark matter. These galaxies remain rare but important, offering unexpected insights into the diversity of cosmic evolution. There could be entire galaxies made mostly of invisible matter. While some galaxies appear to lack dark matter, others might be composed almost entirely of it. Such galaxies would contain very few stars, making them extremely faint and difficult to detect. Their presence could be inferred only through gravitational effects on nearby objects, or through subtle lensing of background light. If these dark-dominated galaxies exist, they might account for a portion of the missing matter in the universe, and provide clues about how dark matter behaves on galactic scales. They might form in regions where normal matter could not cool efficiently, or where star formation was suppressed. Studying them would deepen our understanding of how structure forms in the dark sector and how galaxies assemble under a wide range of initial conditions. Discovering even a few would dramatically expand our view of what counts as a galaxy. They might be stellar objects that do not fit in any known category. Astronomers classify stars into familiar groups based on temperature, mass, and composition. Yet surveys occasionally reveal objects that defy simple categorization. Some appear too cool to be stars, but too warm to be planets. Others show chemical signatures or brightness patterns that do not match standard models. These oddities may represent previously unknown stages of stellar evolution, or entirely new kinds of objects shaped by exotic physical processes.
They could be remnants of unusual formation histories or products of environments not seen elsewhere. Understanding them requires detailed observation and creative thinking about how matter behaves under unexpected conditions. Each new anomaly challenges the boundaries of established classifications, reminding us that the universe may host forms of stellar structure that are rare, fragile, or simply unfamiliar. There could be ancient cosmic structures we have not yet seen. The observable universe contains clusters, filaments, and other large-scale formations. But our surveys cover only a limited portion of the cosmos. Beyond the reach of current instruments, there may be structures older, larger, or more complex than any mapped so far. These might include massive collections of galaxies, unusually shaped regions of cosmic voids, or patterns imprinted by early processes that no longer operate. Some features may be so faint or diffuse that they blend into the background, while others may lie beyond our observational horizon. As telescopes and analysis techniques improve, we may uncover hints of these hidden structures through gravitational effects, subtle distortions of ancient light, or unexpected alignments. Their discovery would deepen understanding of how matter arranged itself across cosmic time. Some stars may collapse in ways we do not understand. Most stars follow predictable paths from formation to final collapse. Yet some observations reveal stellar deaths that do not match standard explanations. Certain explosions appear too bright or too faint for their expected mass. Others produce unusual remnants or emit energy in ways that challenge known physics. Some stars may collapse directly into black holes without visible explosions, while others may undergo partial collapse that leaves behind exotic cores. These anomalies suggest that the internal processes driving stellar endings may involve complexities not captured in current models. Studying such events requires rapid observations, broad wavelength coverage, and careful comparison with theoretical predictions. The diverse ways in which stars reach their final moments reveal that stellar evolution still contains unsolved mysteries. Neutron stars might hide states of matter unknown on Earth. Inside a neutron star, matter is compressed to densities far beyond anything achievable in laboratories. Under such conditions, atoms no longer exist in familiar forms. Electrons are forced into protons, forming an immense sea of neutrons packed together with almost no empty space between them. Yet even this description may be too simple. The pressure in the core could become so extreme that neutrons break down into their constituent particles or rearrange into entirely new states of matter. Some models predict a fluid of quarks, while others imagine strange particles that appear only under the most intense compression. These extreme environments may host behaviors not found in any other place in the universe. Because we cannot probe neutron star interiors directly, we rely on clues from vibrations, cooling patterns, and the way these stars react when paired in binary systems. Each observation offers a hint. Yet the true nature of matter inside remains an unsolved and profoundly compelling mystery. There could be objects denser than neutron stars, but not black holes. The known universe contains white dwarfs, neutron stars, and black holes. But some theories suggest the existence of objects that fall between the last two categories. These hypothetical bodies could be composed of exotic particles or unusual arrangements of matter that resist collapse even at extreme densities. They might be smaller and heavier than ordinary neutron stars, yet not compressed enough to form an event horizon. If such objects exist, they would challenge our understanding of the nuclear forces that hold matter together. Their signatures might hide in puzzling mass measurements or unusual behaviors in binary systems. Distinguishing them from known objects requires precise observations of how they bend light and how they interact with companions. These ultra-dense bodies would provide a natural laboratory for physics beyond the familiar, revealing new layers of complexity in how matter behaves under pressures far surpassing anything seen on Earth. Some neutron stars might convert entirely into exotic matter. As certain neutron stars gain mass through accretion or evolve over long timescales, their internal pressure may reach thresholds where neutrons become unstable. In some models, this instability triggers a conversion to strange matter or quark matter, creating an object radically different from its original form. This transformation could occur suddenly or gradually, altering the star's rotation, magnetic field, and thermal properties. If the entire interior converts, the star becomes a new type of compact object with a different density and structure. Detecting such transitions would require careful monitoring of pulsars for abrupt changes in timing or unexpected shifts in emitted radiation. These conversions, if real, would reveal that nature supports forms of matter more exotic than anything observed in laboratories. The idea that a neutron star can transform from one extreme state to another adds a remarkable dimension to the study of compact objects. There could be planets orbiting neutron stars that should not exist. The discovery of planets around neutron stars came as a surprise, because the violent events that create these compact remnants should destroy or eject any nearby worlds. Yet, several pulsars host planets that orbit steadily, suggesting either remarkable survival or formation from debris after the original star's explosion. These planets experience intense radiation and extreme gravitational conditions, making them unlike typical worlds around ordinary stars. Some may have formed from disks of material shed during the supernova, while others may be remnants of disrupted companion stars. Their unusual origins raise questions about how planets can form or endure in hostile environments. Studying them allows researchers to explore the outer limits of planetary physics and examine worlds shaped by conditions far removed from those that influenced the solar system. These strange planetary systems highlight the resilience and diversity of planetary formation across the cosmos. Neutron star collisions might produce unknown particles. When two neutron stars spiral together and merge, they create some of the most extreme conditions in the universe. Temperatures soar and densities climb, producing an environment where nuclear reactions and particle interactions reach energies far beyond those achievable in particle accelerators. Such collisions may create particles that never appear in ordinary reactions, briefly revealing aspects of physics that remain hidden under normal cosmic conditions. These mergers also send out gravitational waves and flashes of radiation signals that can carry delicate clues about the particles involved. If unknown particles are produced, they could subtly redistribute energy or alter the signatures seen by our telescopes. Each merger becomes a rare chance to study matter at its most extreme, offering glimpses into the behavior of fundamental particles under conditions that existed only for moments in the early universe. Some neutron stars even spin in ways that defy our current understanding of physics. Neutron stars are known for their rapid rotation, yet some exhibit spin rates or timing behavior that challenge theoretical expectations. Certain pulsars maintain astonishingly stable periods, while others glitch suddenly, changing rotation speed in unpredictable jumps. A few spin so fast that their survival seems to defy limits imposed by structural integrity. These behaviors may involve complex interactions among the crust, superfluid interior, and magnetic fields. They might also hint at processes not yet understood, such as interactions with exotic matter or instabilities rooted in quantum phenomena. Observing these spin patterns helps researchers test models of how compact objects evolve, and how their internal layers interact. The diversity of rotational behaviors suggests that neutron stars may host intricate mechanisms that push the boundaries of known physics. There could be pulses of neutron star activity we have never detected. Neutron stars emit radiation across a wide range of wavelengths, much of it highly directional. If their beams do not sweep across Earth, we never observe their signals. Many neutron stars may therefore remain unknown, hidden simply because their emission does not intersect our line of sight. In addition to regular pulses, neutron stars can produce bursts, flares, or subtle vibrations that may be too faint or too brief for current instruments to capture. Some phenomena may require new detectors or more sensitive surveys to uncover. There might be entire classes of neutron star emissions that lie just outside the capabilities of existing technology. Detecting these would expand our understanding of how neutron stars transfer energy, how their magnetic fields evolve, and how their interiors respond to stress. The unseen behaviors of these compact objects likely form a rich and unexplored domain of astrophysics. Neutron stars might hold clues about the universe's earliest moments. Because neutron stars contain matter, compressed to densities similar to those present shortly after the beginning of the universe, studying them offers insights into physical conditions that no laboratory can replicate. Their cores may preserve information about interactions that shaped the early cosmos, including transitions between different states of matter. The behavior of their crusts, magnetic fields, and oscillations reflects fundamental forces that also influenced early cosmic evolution. Observations of neutron stars in binary mergers provide data about how matter behaves at extreme temperatures and densities, echoing conditions from the first fractions of a second of cosmic history. By decoding the signals from these events, scientists hope to learn about forces and particles that operated in the earliest moments. Neutron stars serve as natural time capsules, holding information from epochs otherwise inaccessible. Some neutron stars might be slowly transforming into black holes. As neutron stars age or accumulate matter from companions, they may approach the threshold at which gravity overcomes all internal pressure. When this limit is crossed, the star can collapse into a black hole. This transformation may not occur abruptly. Some models suggest a gradual sequence of internal changes as the star becomes increasingly compact, with phases marked by shifts in rotation, magnetic fields, or emission properties. Observing these signatures might allow astronomers to witness the stages leading to collapse. Such transitions would reveal the fine boundary between the stability of neutron matter and the gravitational pull that forms a black hole. Identifying stars on the brink of this transformation would provide valuable information about the fundamental limits of matter and the complex pathways that lead to the creation of black holes. Neutron star crusts could contain the strongest material in the universe. The outer layers of a neutron star form a crystalline lattice of nuclei packed together under extreme pressure. This material must support enormous magnetic fields and withstand immense stresses caused by rotation and internal motion. Calculations suggest that the crust structure may be hundreds of times stronger than any known substance on Earth. It could deform without breaking, endure intense strain, and store vast amounts of elastic energy. When this crust finally gives way, it may produce sudden changes in rotation or bursts of radiation. Understanding the properties of this remarkable material helps explain how neutron stars behave under stress and why they sometimes experience abrupt shifts. Its strength reflects the unique conditions of these compact objects, where extreme density and pressure create forms of matter that simply cannot exist anywhere else. We still do not know what most comets originate from. Comets carry some of the most ancient material in the solar system. yet their true origins remain elusive. While many are believed to come from a distant reservoir known as the outer cloud, we have never observed this region directly. It lies so far from the Sun that any objects within it reflect almost no light, making them effectively invisible to telescopes. The few comets we see are those that have been nudged inward by gravitational disturbances, but these represent only a tiny sample of what likely exists. Their compositions vary widely, hinting at different birthplaces or histories. Some contain ingredients associated with deep cold environments, while others show signs of processing in warmer regions. This diversity suggests that comets may form in multiple zones or migrate long distances before settling into the far reaches of the solar system. Until we develop ways to detect objects across those extraordinary distances, most of their place of origin will remain a hidden chapter of our solar system's story. There could be entire clouds of objects beyond the reach of our telescopes. Astronomers suspect that the outskirts of planetary systems may hold vast collections of icy bodies far larger in number than the comets and asteroids we observe near the Sun. These distant clouds could contain trillions of small objects drifting silently through space.
Because they reflect so little light and lie at such great distances, they evade even the most powerful telescopes. Their existence is inferred from the behavior of long-period comets and from models of how planetary systems form. These unseen populations may include bodies with diverse compositions, shapes, and histories, each shaped by conditions in the early solar nebula. They could also influence the motion of nearby stars or record subtle gravitational interactions from ancient encounters. Detecting them will require future missions that can sense faint thermal signatures or gravitational effects across enormous distances. Until then, the outermost regions of planetary systems will remain among the least explored realms in astronomy. The space between stars may hold more than dust and gas. Interstellar space is often described as a thin mixture of dust, gas, and radiation. Yet growing evidence suggests that it may contain far more complexity. Observations of absorption lines and faint emissions reveal unexpected molecules, unusual temperature gradients, and hints of structures that do not fit simple models. Some regions appear to host dense clumps of material that drift independently, while others contain magnetic patterns that extend for great distances. There may also be charged particles and tiny grains with properties distinct from those found in the solar system. These components influence how light travels through space, how stars gather material, and how shock waves from supernova propagate. The interstellar medium is dynamic, shaped by stellar winds, radiation, and passing clouds. Understanding it requires combining chemistry, plasma physics, and studies of cosmic dust. Far from being empty or simple, the space between stars may be a vibrant and evolving environment. They could be invisible structures moving through interstellar space. As astronomers map the galaxy, they find variations in starlight that hint at objects or patterns passing between us and distant stars. These features do not match the behavior of known clouds or dust. Some appear transient, shifting on timescales too short for ordinary interstellar material. Others produce effects that suggest large but diffused structures with properties unlike typical gas or dust formations. These invisible shapes might be composed of extremely fine particles, magnetic filaments, or low-density material that interacts with light in unusual ways. They could form naturally through turbulence or arise from processes not yet understood. Detecting them requires repeated observations of the same stars and careful analysis of subtle changes. If such structures are common, they may influence how matter cycles through the galaxy, shaping star formation and the distribution of interstellar material. Their elusive nature highlights how much remains undiscovered in the vast spaces between stars. Some rogue objects traveling through space defy classification. Occasionally, astronomers detect objects moving on trajectories that do not match typical comets, asteroids, or planets. These rogues drift freely through space, unbound to any star. Some may be fragments from disrupted planetary systems, while others might have formed independently in the cold depths between stars. Their properties vary widely. A few show comet-like activity when approaching a star, while others behave more like dense rocky bodies. Some move at speeds that suggest distant or tumultuous origins. Because they do not remain in the solar system for long, studying them requires rapid observation and careful analysis. These visitors offer insights into the diversity of material in the galaxy and the processes that eject objects from planetary systems. Their unusual features challenge existing categories and reveal that the galaxy may hold many forms of wandering bodies we have only begun to identify. Interstellar space may contain reservoirs of frozen, ancient material. Cold regions far from stars allow molecules and dust grains to survive unchanged for immense periods. These reservoirs could hold frozen gases, complex organic compounds, and minerals older than many stars in the galaxy. When such material is disturbed by shock waves or passing objects, fragments may drift into denser regions, influencing star and planet formation. Some of the frozen material may carry signatures of chemical processes that occurred in the earliest phases of the galaxy. These reservoirs also affect the temperature and ionization of interstellar clouds, shaping the cycle of matter between stars. Detecting them is difficult because they emit little radiation, yet faint signals in the infrared and radio bands hint at their presence. These silent storehouses of ancient material serve as archives of cosmic history, preserving clues about conditions that shape the earliest environments in the galaxy. There might be complex magnetic fields spanning vast distances. The galaxy is threaded with magnetic fields that twist, bend, and interact with charged particles. These fields are difficult to map because they do not emit light directly. Instead, they reveal themselves through the behavior of cosmic rays, polarized starlight, and the motion of gas clouds. Some regions show remarkably coherent structures extending through interstellar space, suggesting large-scale organization. Others display tangled patterns shaped by turbulence or shock waves from exploding stars. These magnetic fields influence star formation, guide charged particles, and help regulate the temperature of interstellar gas. They may also shape the boundaries between different regions of the galaxy, creating large but invisible frameworks that affect how matter moves. Understanding these magnetic structures is essential for modeling how the interstellar medium behaves. Yet much about them remains a mystery. Their complexity hints at processes that stretch across immense distances and unfold over extraordinary spans of cosmic time. There may even be waves moving through space that we have not yet recognized. Beyond gravitational waves, which ripple through space-time itself, other forms of waves could be traveling throughout the galaxy. These waves might arise from oscillations in magnetic fields, fluctuations in charged particle densities, or subtle shifts in interstellar pressure. Some may drift slowly through diffuse clouds of gas, while others could race swiftly through regions filled with plasma. Because they emit little or no light, they are difficult to detect with traditional instruments. Yet their presence could shape the birth of stars, influence the paths of cosmic rays, and even alter how material is distributed across the galaxy. Detecting these waves would require sensitive measurements of radio emissions, polarization patterns, or tiny changes in the motion of interstellar gas.
Discovering such hidden waves would reveal new channels through which energy flows across cosmic environments, adding depth to our understanding of galactic dynamics. Exotic molecules may form in interstellar regions where chemistry should fail. Some areas of interstellar space are so cold and diffuse that chemical reactions should be extremely slow. Yet observations reveal molecules that seem too complex to form under such barren conditions. These exotic compounds range from simple organics to surprisingly intricate structures. They may arise from reactions on the surfaces of dust grains triggered by faint starlight or cosmic rays. Alternatively, they might form within transient pockets of denser material that collapse and disperse quickly. The presence of these molecules challenges traditional ideas about where chemistry can occur. Their distribution influences the composition of forming stars and planets. Seeding young systems with raw material that may play roles in later chemical evolution. Understanding how these unexpected molecules form requires a combination of laboratory experiments, modeling, and careful astronomical observation. Their existence highlights the creativity of nature in environments once thought chemically inactive. There might be unseen objects passing through our solar system. The solar system is vast, and many regions remain poorly explored. Objects with extremely dark surfaces or unusual compositions could drift through its outer reaches without reflecting enough light to be detected. Some may follow long, looping orbits that keep them far from the sun for most of their journey. Others might pass through only once, moving quickly and silently before returning to interstellar space. Their gravitational influence on known planets or comets might be too subtle to measure. Detecting such unseen bodies would require wide field surveys capable of spotting faint movement against the background of stars. Future missions that map the sky continuously may finally reveal these hidden travelers. Their discovery would expand our understanding of the solar system's population and shed light on the variety of objects that wander through our celestial neighborhood. The nature of quantum vacuum energy remains a deep mystery. Empty space is not truly empty. According to quantum physics, even the quietest vacuum contains a restless sea of energy that cannot be removed. This energy influences how particles behave and how fields interact. Yet its true origin remains unclear. Calculations of vacuum energy often produce values far larger than anything observed in the real universe, suggesting that something in our understanding is incomplete. This energy might interact with space in ways that affect cosmic expansion, hinting at a possible connection to dark energy. It could also shape how fields fluctuate across vast distances. Because vacuum energy cannot be switched off or isolated, it can only be inferred indirectly through subtle measurements of particle behavior or delicate shifts in atomic states. Every attempt to explain it opens new questions, suggesting that vacuum energy may hold clues to deeper layers of reality that lie beyond current theories. Particles might pop in and out of reality from hidden realms. Quantum theory allows particles to appear briefly, interact, and vanish again, borrowing energy for a fleeting moment before conserving the total balance. These ephemeral phenomena are usually described as fluctuations, yet some researchers explore the idea that they may be linked to realms outside ordinary space. In these views, particles could momentarily dip into hidden layers of the universe before returning, creating short-lived signatures in measurable quantities. If such realms exist, they could host structures or fields that influence our world only through these brief interactions. Detecting these events directly is nearly impossible because they occur on unimaginably small scales and over extremely short intervals. Instead, Scientists search for tiny deviations in particle collisions or unexpected patterns in the behavior of quantum fields. These fleeting appearances hint that the universe may include unseen dimensions that leave only the faintest traces. Quantum processes could influence the entire cosmos. Although quantum physics typically governs the world of the very small, some processes may have effects that ripple through the universe on enormous scales.
Fluctuations in quantum fields during the earliest phases of cosmic history might have seeded the large-scale structure of galaxies. Tiny variations could have grown into the clusters and voids visible today. Quantum tunneling might also play roles in processes that affect the lifetime or evolution of the cosmos. Even the stability of space itself could depend on quantum interactions occurring throughout the vacuum. These possibilities suggest that the behavior of particles and fields on minute scales can shape the universe's fate. Understanding these influences requires bridging the gap between quantum theory and cosmology, two domains that operate under vastly different conditions. Their intersection remains one of the richest and most mysterious areas of modern physics. We do not know whether reality is continuous or pixelated. Mathematics often describes space and time as smooth and continuous. Yet some theories propose that at the smallest scales, they might be composed of discrete units. These tiny building blocks could determine the limits of how finely space and time can be divided. If reality is pixelated, then notions such as position, motion, and energy may behave differently near these fundamental scales. Experiments that probe extremely short distances or high energies are necessary to test this idea. Yet achieving such conditions is far beyond current technology. Indirect hints may come from the behavior of gravitational waves or from subtle anomalies in the motion of particles. Determining whether the universe is continuous or discrete would reshape our understanding of geometry, physics, and the nature of space-time. It remains one of the deepest unanswered questions in theoretical science. The universe might be haunted by virtual particles we cannot observe. Virtual particles constantly influence measurable properties, even though they do not appear in ways detectable as ordinary matter. They modify forces, shift energy levels, and alter how particles interact. These unseen contributors arise naturally from quantum fields that fill space, flickering into relevance only during specific processes. Though they vanish almost immediately, their effects accumulate across countless interactions, subtly shaping everything from atomic transitions to the behavior of electromagnetic fields. Virtual particles may also play roles in more mysterious phenomena, such as the vacuum energy problem or the behavior of space under extreme conditions. Their existence reveals that much of reality operates through hidden processes that can be inferred only through their influence on observable quantities. Understanding them forces physicists to accept that unseen layers of activity underpin the physical world. Quantum fields could be more fundamental than space itself. Some interpretations of physics treat quantum fields as the primary ingredients of reality, with particles emerging as excitations of these fields. In this view, even space may not be a fixed stage, but a phenomenon that arises from deeper interactions among fields. The geometry of the universe, the strength of forces, and the behavior of matter could all be consequences of patterns embedded within these fields. If this perspective is correct, then space might not exist independently, but instead emerge from relationships among more basic components. Evidence for this idea appears in attempts to unify gravity with quantum theory. Some approaches suggest that space-time curvature reflects how information or entanglement is distributed within quantum fields.
Uncovering the precise structure of this deeper layer remains an enormous challenge. Yet, its implications would transform our understanding of the universe.
Quantum uncertainty might shape the large-scale structure of the universe. Quantum uncertainty dictates that particles cannot have perfectly defined positions or energies. During the universe's earliest moments, this uncertainty created tiny irregularities in the distribution of matter and energy. Over cosmic time, gravity magnified these tiny irregularities, causing some regions to expand into galaxies, while others stretched into enormous voids. In this way, the large-scale structure of the universe may trace its origins back to random fluctuations at the quantum level. Even today, quantum uncertainty may influence processes such as the behavior of black holes or the properties of dark energy. The connection between microscopic unpredictability and the vast architecture of the cosmos shows just how far quantum principles reach. Understanding this relationship requires studying ancient cosmic light and running simulations that follow how the smallest variations grow into immense structures. The idea that randomness on the tiniest scales helped shape the entire universe remains one of the most extraordinary insights in modern science. There could be unknown quantum states filling the entire cosmos. Quantum fields can occupy many possible states, some familiar and others never observed directly. The vacuum itself may represent only one configuration within a much larger landscape of possibilities. If the universe contains regions where fields settle into different states, these variations could influence the strength of forces, the masses of particles, or the behavior of space. Such states might be stable, long-lived, or ephemeral, leaving faint imprints on cosmic history. They could shape how matter formed, how galaxies evolved, or how the universe expands. Detecting them is extremely difficult, because their signatures may be subtle or hidden within the background of known phenomena. Nevertheless, their existence is supported by some theoretical models that seek to explain the diversity of physical constants. Unknown quantum states may operate quietly throughout the cosmos, influencing reality in ways we have not yet recognized. Quantum effects might affect gravity in extreme situations. General relativity describes gravity as the curvature of spacetime. Yet at very small scales, or under extreme conditions, quantum processes may alter this behavior. Near the centers of black holes, or in the earliest moments of the universe, the smooth geometry predicted by relativity may break down. Quantum fluctuations could produce irregularities, distortions, or limits on how sharply space can curve. These effects might prevent singularities or change the fate of collapsing matter. They could also influence how gravitational waves propagate or how black holes evaporate. Studying such situations requires combining quantum theory with gravity, a task that continues to challenge physicists. Although indirect hints appear in theoretical models, direct evidence remains elusive. Understanding how quantum processes modify gravity would open a window into the deepest workings of the universe. Reality might depend on information in ways we do not yet understand. Emerging ideas in physics suggest that information could play a central role in shaping reality. In this view, the properties of particles, the behavior of forces, and even the structure of space may reflect patterns of stored or distributed information. Some theories propose that the universe's geometry arises from networks of quantum entanglement. Others argue that physical laws follow from principles of information preservation. These concepts connect areas once thought unrelated, linking thermodynamics, quantum mechanics, and gravity. Evidence appears in the behavior of black holes, which seem to store vast amounts of information in unexpected ways. If reality is indeed governed by informational principles, then matter and space may be secondary expressions of deeper rules. Understanding these rules would revolutionize physics, offering a new framework for exploring the universe. Vast radio bursts might come from processes we have never considered. Fast radio bursts are brief flashes of radio energy that last for only a fraction of a second. Yet in that instant, they release more power than many stars produce in long stretches of time. Their origins remain deeply mysterious. Some repeat, others fire only once, and many appear from directions with no obvious source nearby. While theories range from magnetars to collisions to strange plasma behaviors, the diversity of signals suggests that at least some may come from mechanisms not yet imagined. Their extreme brightness hints at compact sources, but their patterns sometimes show irregularities that challenge existing models. Because they travel across vast distances, they carry information about the medium between galaxies. Yet that information is difficult to interpret. Some bursts arrive with structures too complex for current explanations. As new instruments capture more events, the puzzle deepens, pointing to physical processes that may stretch or reshape our understanding of cosmic energy. Some cosmic signals could originate from unknown natural engines across the sky. Telescopes detect signals that do not fit cleanly into known categories. Some are too sustained to be bursts, yet too irregular to be typical emissions from stars or galaxies. These signals may arise from natural engines that have not yet been identified. Extreme magnetic fields, turbulent environments, and interactions between exotic particles could generate emissions unlike any familiar process. Some signals vary in brightness or frequency in ways that do not correspond to standard astrophysical cycles. Others show sudden changes that hint at hidden mechanisms operating deep within cosmic structures. The galaxy may host dynamic engines that activate under conditions we have not yet observed directly. Understanding these signals requires gathering more data, refining analysis methods, and keeping an open mind about processes that may exist outside established frameworks. Each unexplained pattern offers a clue to unseen behavior in the universe. There might be flashes of energy we have not learned how to detect. The universe produces many kinds of emissions, yet our instruments detect only a narrow range of possible signals. Some energy bursts may be too faint, too brief, or emitted at wavelengths beyond the reach of existing technology. These flashes could occur during rare cosmic events or in environments where matter and radiation behave in unfamiliar ways. They might carry information about extreme physics, exotic particles, or transitions that occur deep within compact objects. If we lack detectors tuned to the right frequencies, these events pass unnoticed. As new observatories expand sensitivity across previously unexplored ranges, astronomers may uncover flashes that reveal unknown processes. Hidden bursts could help explain unexplained cosmic variations or missing energy signatures. The possibility that entire classes of events remain invisible underscores how much of the universe operates beyond our current perception. Some cosmic rays arrive with energies we cannot explain. Cosmic rays are high-energy particles that strike Earth from space. Most originate from known processes, such as supernova remnants or active galaxies. Yet a small fraction arrive with energies far too high for these sources. These extreme particles challenge theories of acceleration because no known environment appears capable of imparting such incredible energy.
They may arise from rare cosmic phenomena, interactions involving exotic particles, or processes that occur near the boundaries of extreme astrophysics. Their paths through space bend under magnetic fields, making it difficult to trace them back to their origins. This obscures the nature of the mechanisms that launched them. Studying these rare particles may reveal new physics operating at energies far beyond those produced by any human-made accelerator. They represent one of the most direct windows into high-energy processes that the universe keeps largely hidden. They could be signals hidden in the noise of the universe.
Astronomical data contains vast amounts of background noise, created by natural processes such as dust emission, cosmic microwave radiation, and faint starlight. Within this noise, subtle signals may be buried. These signals could originate from phenomena too weak or too rare to stand out clearly. Some might be patterns that repeat only over long timescales, while others might appear as barely detectable variations. New analysis techniques using advanced modeling and machine learning may help uncover these hidden signs. If such signals exist, they could reveal unknown objects, transitions, or interactions. They might also provide clues about processes that shape the early universe or influence cosmic structure today. The possibility that important information lies concealed within noise adds depth to the challenge of interpreting astronomical observations. Some gamma-ray bursts might reveal unknown cataclysms. Gamma-ray bursts are among the brightest explosions known, often linked to collapsing massive stars or merging neutron stars. Yet, a subset of these bursts do not match established categories. Their durations, intensities, or afterglows differ from expectations. Some appear too short for stellar collapse, yet too long for known merger processes. Others lack expected signatures in lower energy wavelengths. These anomalies suggest that additional kinds of cosmic cataclysms may exist, involving mechanisms not yet understood. They might arise from exotic stars, unusual magnetic events, or interactions involving compact objects in unexpected configurations. Because gamma rays carry enormous energy, even small differences in their emission mechanisms reveal profound variations in underlying physics. These unusual bursts may hold clues to rare or extreme events that occur infrequently but shape the evolution of energetic regions of the universe. There could be rhythms in cosmic activity we have not yet noticed. Across the cosmos, many processes follow cycles, from stellar pulsations to galactic interactions. Yet some rhythms may be so slow, faint, or irregular that they escape detection. These long-term or subtle cycles might govern changes in magnetic fields, variations in emission from compact objects, or shifts in large-scale cosmic structures. They could also operate on timescales far longer than human history, making them difficult to observe without continuous, long-term monitoring. Detecting such rhythms might require observing many objects simultaneously or analyzing historical data for patterns. If these cycles exist, they could reveal coordinated behavior across distant regions or provide insights into processes that evolve gradually. Cosmic rhythms may be hidden background patterns shaping the dynamic behavior of the universe. Some astronomical events might repeat on timescales longer than human history. Certain cosmic phenomena occur so infrequently that no human has witnessed more than a single instance. Ancient star eruptions, rare collisions, and slow changes in stellar interiors may repeat only after long intervals. Some stars may undergo dramatic transformations on cycles lasting thousands or millions of years. These events could influence surrounding environments, trigger waves of star formation, or reshape cosmic structures. Because these timescales extend far beyond recorded observations,
it is difficult to confirm whether certain phenomena repeat or are singular occurrences. As data accumulates over generations, astronomers may begin to detect signs of cyclic behavior. Understanding these long-term processes will reveal how objects evolve over deep time and how seemingly stable systems undergo changes on scales that transcend human experience. There might be transient phenomena too brief for current instruments.
Many astronomical events occur in the blink of an eye, releasing energy in extremely short bursts. If these flashes last only microseconds or nancans, current detectors may not be fast enough to register them. Such transient events might arise from rapid magnetic reconnection, particle interactions in extreme environments, or collisions involving small bodies. Detecting them requires instruments with very high temporal resolution and continuous monitoring. Because they vanish almost instantly, their properties may differ significantly from longer events. These fleeting phenomena may play important roles in transferring energy, shaping radiation fields, or influencing cosmic environments in ways not yet understood. Discovering such signals would broaden the known spectrum of celestial behavior. The universe may emit faint glows from processes that fall outside the boundaries of current physics. Some portions of cosmic radiation could arise from mechanisms that do not fit within today's particle physics or astrophysical models. These glows might appear as diffuse light spread across vast regions, or as subtle backgrounds produced by unfamiliar interactions. They could originate from exotic particles, transitions in quantum fields, or processes connected to dark matter. Their spectra would differ from starlight or normal thermal emission, making them difficult to spot within existing data. Detecting them requires carefully separating known backgrounds and approaching faint signals with fresh, creative methods of interpretation. If confirmed, these glows could reveal entirely new categories of energy release phenomena that operate quietly throughout the universe. Life might arise in conditions completely foreign to us. On Earth, life depends on liquid water, moderate temperatures, and a familiar set of chemical reactions. Yet, the universe contains environments far outside these boundaries. There are worlds with crushing pressures, extreme cold, violent radiation, or atmospheres filled with chemicals toxic to known organisms. In such places, life could emerge through pathways unlike anything in terrestrial biology. Reactions that fail in Earth-like settings might flourish under different conditions. Energy could come from sources unrelated to sunlight, such as deep chemical gradients, magnetic interactions, or slow geological processes. Structures that resemble cells might form from exotic materials that behave predictably only under extreme conditions. These possibilities force us to consider that life is not a narrow phenomenon, but a process shaped by its environment. If such unfamiliar life exists, detecting it will require methods that do not rely on assumptions drawn from a single example. It expands the search for living systems into realms we once dismissed as barren. The building blocks of life could form in places we would not expect. Complex organic molecules appear in interstellar clouds, on icy comets, and within the atmospheres of giant planets. These environments seem inhospitable, yet they host chemical reactions that produce ingredients essential for life. Radiation, cold temperatures, and dust grains provide surfaces and energy sources that drive unusual chemistry. Some clouds contain long carbon chains, while cometary ice traps molecules that may have formed in ancient cosmic regions. Even gas giant atmospheres show hints of compounds that could serve as precursors to biological structures. These materials may later seed young planets or accumulate on surfaces where conditions eventually allow life to develop. The universe seems to be a factory for organic components, producing them across environments with no resemblance to Earth. Understanding these processes helps explain how life's essential ingredients may arise long before planets are ready to host living systems. The universe might host life based on chemistry we do not yet understand. Life on Earth uses a narrow set of molecules built around carbon, hydrogen, oxygen, and nitrogen. Alternative forms could rely on entirely different chemistries. Some environments may support molecules that remain stable only under extreme pressures or temperatures. Solvents other than water could permit reactions that assemble structures unfamiliar to terrestrial biology. Elements such as silicon, sulfur, or phosphorus might form the basis for self-sustaining systems that process energy and replicate. These hypothetical life forms would not resemble microbes, plants, or animals. Their metabolic pathways, structural components, and modes of growth could be unrecognizable. Detecting such life requires moving beyond Earth-centered assumptions and considering signatures based on unexpected patterns in heat, chemistry, or energy flow. The variety of possible chemistries suggests that life may exist in forms that challenge every definition currently used in science. Life elsewhere could evolve in environments we cannot imagine. Planets and moons throughout the universe experience conditions far different from those found on Earth. Some are locked in perpetual darkness, while others endure long cycles of intense heat and extreme cold. Certain worlds have thick atmospheres, boiling oceans, or surfaces coated in exotic materials. Life, if present, would adapt to these conditions using strategies shaped by unique evolutionary pressures. Organisms might rely on energy from tidal forces, deep interior heat, or chemical gradients created by unusual minerals. They might develop structures suited for dense atmospheres or low gravity. Evolution could produce behaviors and sensory systems unlike anything on Earth. Considering such diversity widens the scope of what living worlds may look like and prepares us to recognize life even when it emerges under extraordinary conditions. There could be biological processes happening in extreme cosmic settings beyond planets. Biological activity might occur in environments that seem completely unsuitable. Certain asteroids contain materials that could support simple chemical cycles. Subsurface oceans on icy moons may host thermal vents where living systems take root. Free-floating objects in interstellar space could contain internal heat sources, maintaining pockets of liquid beneath icy crusts. Even dust-laden clouds may shelter molecules capable of developing into primitive systems. These possibilities show that biology might not require stable surfaces or traditional planetary conditions. Instead, it could arise wherever chemical complexity and energy sources align. Studying these environments expands the search for life into regions previously considered irrelevant for biology. Life might leave traces we do not yet know how to recognize. Most searches for life rely on signatures familiar from Earth, such as oxygen, methane, or chlorophyll-related pigments. Yet, alien life may produce byproducts unlike anything found in terrestrial ecosystems. It might release gases that appear inert or unimportant, create patterns in heat emissions, or alter minerals in subtle ways. Such signatures may blend into background noise or be dismissed as ordinary geological effects. Recognizing them requires new frameworks that consider a wide range of possible biosignatures. These may include unusual chemical ratios, unexpected atmospheric cycles, or repeating patterns not caused by natural processes. Understanding how life alters its environment in unfamiliar ways will be crucial for identifying living systems
across the universe. The universe could host civilizations with unknown technological signatures. If intelligent life exists elsewhere, its technologies may not resemble radio transmissions, satellites, or optical signals. Advanced civilizations might use energy sources invisible to current detectors, or construct structures that blend into natural backgrounds. They could manipulate magnetic fields, reshape planetary atmospheres, or leave imprints in radiation fields that appear natural to us. Their communication methods may not rely on electromagnetic waves at all. Technologies based on principles we have not yet discovered might operate across scales or frequencies outside human detection capabilities. Searching for such civilizations requires expanding our expectations beyond familiar ideas. Unknown signatures may be hiding in existing data, waiting for new perspectives to reveal them. Some worlds might hold ecosystems entirely unrelated to our own. On distant planets, ecosystems could develop with species that do not share Earth's genetic or biochemical foundations. Their interactions might follow rules shaped by alien environments, such as constant storms, dim starlight, or abundant minerals unknown on Earth. Food webs. Organisms could use materials that are unstable in terrestrial conditions, forming tissues and structures that behave unpredictably when compared to Earth-based life. Such ecosystems would rewrite our assumptions about how living communities form, interact, and evolve. Their discovery would offer insight into the adaptability of life and the range of ecological possibilities available across the universe. Life could exist in forms that do not rely on planets. Floating habitats in interstellar space, suspended environments within giant planet atmospheres, or stable structures around stars could all support life. Some systems may provide heat and chemical gradients without needing a solid surface. Life might arise in clouds of organic particles, or within long-lived vortices in thick atmospheres. It could occupy magnetic structures or exist within networks of complex molecules drifting through space. These possibilities challenge the idea that planets are the primary homes for biology. Instead, life may thrive wherever conditions allow complexity and energy flow, even if no planet is present. The universe may reveal forms of life that change our idea of what life is. As we explore more worlds and detect more signals, we may encounter systems that blur the line between life and non-life. These forms could challenge the definitions used in biology, forcing scientists to rethink concepts such as metabolism, growth, and reproduction. Some systems might rely on processes unfamiliar to Earth's chemistry, while others might operate at scales too small or too large for traditional categories. Discovering such life would expand the boundaries of science, offering new perspectives on how matter organizes itself into living patterns. The universe may hold examples that redefine the very meaning of being alive. As we drift to the end of our quiet journey, take a moment to feel how wide the universe truly is. Every mystery we explored tonight is a reminder that our understanding is still young. Even after all the discoveries made by science, so much remains hidden in the deep, dark spaces between the stars. Every unanswered question is an open door. Every strange signal or unusual pattern is an invitation to look closer. The unknown is not something to fear. It is a landscape that keeps expanding the more we explore it. If this gentle journey into the unknown brought you a moment of calm, I invite you to like, subscribe, or share a thought below. It helps others find their way here as well. one sleepy soul at a time. And now, let the quiet settle around you.
Let your thoughts soften. Allow the weight of the day to slip away as the night folds itself gently around your shoulders. There is nothing left to solve, nothing you need to carry, only the slow ease of wandering thoughts and the soft rise of rest meeting you exactly where you are. Good night.